Hello, my name is Steven Gardner.
Hi, my name is Dylan Sun.
Hello all, my name is Daniel Gomez Valdez. I am here to showcase the drone that we have designed as part of a swarm of drones that will help in the event of a disaster. Our aim is to minimize the time emergency personnel can arrive at the site of disasters. Clearing roads to get to certain locations can be delayed for hours, as well as reducing the fatigue for search and rescue personnel that have to carry heavy load of equipment with addition to their already heavy PPE. So again, to as an introduction, one of the major aspects for the search and rescue is that their mission has been heavily impacted by the lack of adequate support, leading to increasing rescue times, and the need for rescuers has also increased. Many search and rescue teams have been losing members to this. So our solution, based on the information, is that there is a clear need for search and rescue to have help. And we'll be doing this through three types of robots. One that will do an aerial infrared robot scan for a wide area to search for people, another aerial drone for cargo, and this is to assist with heavy equipment or some type of lifting, air sampling and chemical sampling, and heat signaling robot. Um, so again, one of the main issues commonly prevalent in search and rescue is the difficulty to go through terrain. As stated in the Oregon Police Department, is due to difficulty in terrain, down trees, hazardous atmospheres. It takes up to 7.5 hours for search and rescue teams to rescue people, in this case hikers, as well as firefighters. Their weight can greatly shift between 75 pounds on their PPE alone. That's not even including their breathing apparatus that can add significantly more weight, plus whoever they have to carry out of a burning building. Um, as well as medical bags for medical personnel. They can weigh between 25 to 45 pounds, and that's not including what other types of items they need to carry. Our target audience is many in the search and rescue operations that lack the necessary resources, from anything from lack of manpower, rough terrains if they have to go through them, or landscapes. Also, who have trouble getting to their rescue site and having delays, or robots. They would target these type of sectors. So the requirements for the drones is for them to be small enough to arrive virtually anywhere and land as necessary. They need to be affordable because these are going to be a lot of departments who are already tight on their budget. For my robot, it will need to carry several items needed for search and rescue with a minimum of 50-pound requirement and able to last a long time for a minimum of 8 hours.
Hi, my name is Dylan, and this is the obstacle robot that I created. As you can see here, here's the CAD model of all the major components. Some of the major components include the DC motors. So as you can see, there's 8 wheels in total, 4 on each side. However, I only have one DC motor powering one wheel on each side. As far as the sensor inputs go, I'm using a proximity IR sensor as well as a regular proximity sensor. Inside of the entire casing is the electronics and a solenoid. What the solenoid does is it will pump up this obstacle jack in order to lift up certain objects. And here is the side view of my robot. As you can see, the robot is fairly large in size. It's around 8 foot in length, 4 feet in height, in order to lift up heavy obstacles. As far as the circuitry for my obstacle robots, I am using a few electrical components. In order to power the robot, I am using a 9-volt battery to power the entire circuit. I'm also going to be using two DC motors that is controlled by the Arduino. And this chip in the middle allows me to control both motors at the same time with just that one board. As far as the inputs go, I'm going to be using an proximity sensor and a proximity motion sensor. Another input I am using is going to be this button right here. It's going to allow for manual inputs from the user. And last but not least, to power the jack and to move it, I will be using a servo actuator, and this is going to be hooked up in series with the button. So here is my activity diagram and code for my obstacle robot. Just a little background on what my robot does. It essentially follows a rescuer into the area that needs to be assisted with. And what its main function is it can lift obstacles up, which allows the rescuer to move around the obstacle and move it out of the way. And so here's the flow chart of my robot. And so essentially the robot starts with everything off, motors are off, and it will first check the inputs from two sensors. It's going to check if anything is moving in front of the sensor, which is from the PIR sensor, and then it will check with the distance sensor. So the robot will check if any objects are within 10 feet of the robot. If these two conditions are satisfied, the motor will turn on and will proceed to follow the rescuer. And so eventually, if the rescuer encounters an obstacle, the rescuer can push a button that will initiate the lifting jack. And so once the button is pushed and the distance sensor recognizes that there's something within 1 foot, the lift jack will turn on and essentially lift the object. And so you can see that if any of these conditions are not satisfied, the conditions will go back to the motor being off, and then it will restart the loop and check to see if any of the sensors are inputting again. So here's a demonstration with Tinkercad of my code and my circuitry. And so the main sensor I'm using is a proximity sensor. And so what happens is the proximity sensor will recognize if an object is within 10 feet of the robot. And if the object is within 10 feet and the proximity sensor senses that something is moving in front of it, which is a human, the motors will start running and it will follow the human. And then the distance sensor will also recognize that if there's an object within 1 foot and the proximity sensor is off, this button can be pushed and the servo actuator will actually move the jack, which will move the obstacle out of the way.
So here's my drone. As you can see, it has 4 propellers. It is very simple carrying drone. It would have a light indicator, dual sensors for forward or proximity and bottom, or proximity to the ground. It would have a pulley system and it would have landing gears. The drone is relatively small, no bigger than a person itself. It's going to be about 6 feet in length, 4 feet in height, and about 5 feet in wide. Here is the circuitry for my drone. It is going to be 2 pulley systems, the clamping mechanism as seen here, landing mechanisms, and the bottom and forward sensors. Here on the code, it is pretty much stating that if the sensors need to be within a certain distance in order for the drone to safely drop their equipment, as well as reading sensors in order for it to land safely. It also has coding for the central hub, so if there's any commands sent to the drone, it would act as such. As mentioned before, here is my circuitry. We're going to start the code. As we start it, we're going to see that we have the forward sensor, the bottom sensor, a light indicator to show that the drone is active and ready to take commands. We got our landing gear and our servo motor for a clamping mechanism. We also have motors here that go clockwise and counterclockwise to simulate the pulley being dropped off or pulled back into the drone, and a manual bypass that lets the drone be accessed remotely. So if we see here, we're gonna do the code needs to read of a distance in the forward within 60 inches, which is about 5 feet, and the bottom to be 96 inches from the ground in order to drop off equipment safely. So if we send the code from the command center, it's going to read the distances, and then you'll see here the motors are actuated. Let's see, we're not within the parameters. Send the code again, and nothing will happen because it's too close to the ground and not safe to drop. We do another code to pick up the equipment. The motors will go in reverse to simulate the package being picked up. If we go back and press the button here, it's going to read the button, and then the motors will go to simulate manual access to it. We're going to go to the clamping mechanism, and we're going to put the code to unclamp because right now it's clamped. We sent the code gets read, the robot will unclamp. Same as putting another code, and we are unclamped. Here for the landing mechanism, we'll solely rely on the bottom sensor, and this is for the sensor to read anything under 36 inches, which is about 3 feet, and that's when the landing mechanism will go forward and actuate in order for the drone to land safely. And this is my basic circuitry. I hope you all enjoyed the simulation. Thank you.
Welcome, my name is Stephen Gardner, and I'll be demonstrating for you the drone I designed, the Hound SNR Flying Wing UAV. So this drone is designed to fly a search pattern with a FLIR camera, and when it comes across a body with a human temperature, it will pull GPS coordinates from its circuit and send it back to the central hub. This wing is made of expanded polypropylene. It's very cheap, very durable, crashes several times, and even if it breaks, it's very cheap and easy to replace. It has much better range being a flying wing than, say, your hobby drone that has 4 rotors and flies like a helicopter. From this view, we see that we have in the nose the FPV cam, first person view, and a FLIR camera, and we also have a pusher prop in the back to propel it. From the back view, we can see where our 2 servos would sit, and these will move the ailerons. The drone uses the ailerons to both steer and to gain and descend in altitude. This is the airfoil I chose. It's a general all-around airfoil that hobbyists will tell you works good for flying wings. We have some drawings here. We see that we're about 2 meters wide. We're about half a meter long, and we're about 55, 60 millimeters thick. This is a mock-up using Arduino of a commercial flight stack, flight controller that we'll be using. We also have a Arduino mock-up of what the FLIR camera would do. Attached to GPS. In this case, we're simulating all of that. From our flow chart, we can see from the start, the central hub inputs what grid it wants to search to the drone. The drone takes off, ascends to 40 meters, levels out, and flies its search pattern. While the drone is flying its search pattern, the FLIR camera is scanning the ground. And when it meets something that's between 35 and 42 degrees Celsius, basically the high and low range of what a human body might be, it sends the GPS coordinates of its location back to the central hub, so the central hub can send rescuers towards it to make sure or to see if it's a person or not. After the pattern is complete, the drone navigates itself back to the hub, and before it reaches the hub, it turns off the engine and then basically glides into the location where the central hub is at. So I'll demonstrate the circuits for you now. We'll start with the flight controller. So immediately the drone asks you, which grid would you like to search? We'll search the first grid. Now it's getting simulated altitude data. Normally flight controllers will have its own altitude. Once it ascends to the proper altitude of 40 meters, we can see that the individual servos go back and forth. This is simulating flying an area, turning around, flying the area next to it. And eventually, when it's done, it starts descending. And then when it's close, it turns off its engine and then it glides right back to you. Now we'll take a look at our FLIR circuit. What happens is we used a temperature sensor to simulate the FLIR camera and then an LED that lights up to indicate that we're sending GPS coordinates to the central hub. So we'll watch our serial monitor. We'll start the simulation and we're reading back a temperature. So let's move our slider into that 35 to 42 degree range. Our LED lights up, meaning we're transmitting data. And then if we look at our serial monitor, we'll stop the simulation. We see that there's a possible survivor / missing person, and that it has GPS coordinates, which are coincidentally very close to ASU campus.
So here's the collective behavior of all three of the robots together as a swarm. So initially, the aerial drone will survey a given area that is provided by the search and rescue team. And so this aerial drone has an IR camera that will give the correct GPS coordinates of the person that needs to be rescued. Based on the GPS coordinates, it is then fed back to the command center, and the command center will use these coordinates and it will give it back to the aerial inventory robot as well as the ground robot. The aerial inventory robot will use these coordinates to carry the rescue supplies so that the human rescuers will not have to carry it. The ground robot will assist the human rescuers to the coordinates of the person in need. The ground robot will also provide obstacle moving capabilities if any are needed.
I'm here to make the business case for our search and rescue drone swarm. You'll notice on the slide that there are a number of public and private entities that would be interested in such a swarm. These swarms are designed to be inexpensive and efficient. Therefore, it's easy on the budget and helps the manpower get more done with less. So emergency workers who are stretched thin over an area due to natural disaster can be even more effective. And we believe that this will make our products attractive to these buyers.
All in all, we learned a lot as a team working together on this project. One of the key points that we took from this project was that communications is extremely important in working on projects in engineering teams, especially when everybody is working in different times and different time zones. Making sure that communication is top priority is extremely important. Another aspect that we learned was that everybody needs to contribute and commit to the deadlines that are set, especially because we're also working online. It's very important that people are on the same page and they contribute at the same time and they have the same deadlines. I feel like next time it's better for us to thoroughly plan things before we start working on our project deliverables. I feel that if we took more time in the planning phase, we could have put out better quality work. In summary, our presentation includes the CAD models, the circuits, and the code for each of our individual robots. All three of our robots perform different functions, including the 2 aerial robots and the 1 ground robot. These 3 robots together will work together on search and rescue missions in order to help people that are in emergency situations.